Welcome back to the Deep Dive. Today we're tackling something really fundamental. We're diving into Richard Feynman's first chapter of 6 easy pieces, the one called Atoms in Motion.
Yeah, it's foundational stuff. Our goal today is basically to get you right to the heart of modern science using Feynman's own approach. He kicks things off with a really profound thought experiment.
Oh yeah. Yeah.
He asks, imagine all scientific knowledge is wiped out, gone, and you can pass only one sentence to the next generation. What single sentence holds the most scientific information?
Wow. Okay. That really frames it. That's the mission then. Find that sentence. But first, Feynman points out why we can't just learn the final perfect laws of physics from the start, right?
Exactly. There are a couple of big reasons. First, well, we just don't know everything yet. Science is always pushing into ignorance, finding out new stuff.
Right. It's not a finished book.
Not at all. And
Right.
second, the laws we do understand often need really advanced math and, very specific language. You can't just dive straight in. So we learn step by step using approximations.
Approximations. That sounds like settling for less than the truth.
Not exactly settling. It's more like building understanding with models we know are useful, but maybe not perfect. It's a key idea in science, actually. Everything we think we know is, well, potentially subject to refinement.
Like the idea about mass. That used to be simple. Mass is constant. Full stop.
Yeah, for ages that was the law, but now we know it's not quite right. Mass actually increases with velocity.
But only when you get really, really fast, near the speed of light.
That's right. So for everyday stuff, the change is tiny, almost zero. You might think, okay, who cares?
But Feynman's point is bigger, isn't it?
Much bigger. Even a tiny, tiny effect like that, quantitatively small, can force a huge change in how we think about the world, our whole picture of reality.
So it forced us to change ideas about space and time.
Fundamentally, even if your car doesn't noticeably get heavier, it teaches us, we have to be flexible, always learning what we know, how well we know it, and how it all fits together.
Okay, so that leads us to the sentence, the big one. The atomic hypothesis. What is it?
All right, here it is, boiled down. All things are made of atoms, little particles that are always moving, always in perpetual motion. They attract each other when they're a little distance apart, but they repel strongly if you try to squeeze them too close together.
That's it. That one sentence.
That's the core idea. And packed into that is basically the explanation for structure, forces, energy, chemistry, phases of matter, just about everything.
To really get it, though, we need to try and visualize these atoms,
Mm-hmm.
which is, well, impossible normally.
Right. So Feynman gives this great analogy. Imagine a drop of water. Magnify it 2,000 times. Now it's maybe 40 feet across, big enough to see tiny living things, maybe paramecia swimming around.
Okay, I can picture that, like a giant fishbowl.
Kind of. But now, keep going. Magnify it way more. 1 billion times.
1 billion. That's enormous.
Yeah, the drop would stretch like 15 miles wide. And it wouldn't look smooth anymore. Forget smooth water. You'd see, as Feynman puts it, this teeming, jostling crowd. Billions and billions of tiny objects bumping into each other.
And those are the water molecules.
Those are the molecules, and each one, if you could zoom in even more, has a structure. Feynman pictures it as like one black ball for oxygen with 2 smaller white balls for hydrogen stuck to it. And they're constantly jiggling, twisting, vibrating in 3 dimensions, held together but resisting being squashed.
And they are just unbelievably small. What was the scale? Angstroms?
About 1 or 2 angstroms, yeah. Which is 10 to 10 meters. So incredibly tiny. Here's another way to think about it. Imagine an apple. Now blow it up, magnify it until it's the size of the entire Earth.
Okay, planet-sized apple. Got it.
Right. The atoms inside that planet-sized apple would then be about the size of the original apple you started with.
Wow. Okay. That really puts it in perspective. It's a whole different world down there.
It absolutely is.
So if everything's made of these jiggling, attracting, repelling particles, how does that simple idea explain the different states of matter? Like liquid, gas, solid.
Let's take water again. As a liquid, the attraction between molecules is strong enough to keep them together, so it has a definite volume. But the jiggling, that's heat, thermal energy, gives them enough motion to constantly slip and slide past each other.
Which is why it flows.
Exactly, that's the flow. Now, add more heat. Increase the temperature. What happens?
They jiggle faster.
Faster and more violently. Eventually, the jiggling becomes so strong it overcomes the attraction holding them together. They break free and fly off in all directions.
That's gas, steam.
That's steam. And the amazing thing about steam, or any gas really, is how much empty space there is. If you could see it, it's mostly void, with these molecules just zooming around randomly, bouncing off each other occasionally.
And bouncing off the walls of a container.
Oh.
That's pressure, right?
Precisely. Pressure isn't some static force. It's the result of this relentless, continuous bombardment. Trillions of tiny molecules hitting the surface every second.
Like tiny invisible tennis balls, as Feynman says.
Exactly like that. So if you cram more molecules into the same space, increase the density, you get more collisions per second. Pressure goes up.
Makes sense.
And if you heat the gas, the molecules move faster, so they hit the walls harder, and they hit more often. Again, pressure goes up.
Okay, that connects temperature, density, and pressure. What about that effect when you compress a gas? Like pumping up a bike tire, the pump gets hot. Why?
Good question. Think about the piston moving into the cylinder, compressing the gas. When a gas molecule hits that piston, which is moving towards it,
It bounces off faster.
exactly, it picks up speed, picks up kinetic energy from the moving wall. It's like hitting a ping pong ball with a paddle that's moving forward. The ball shoots off faster.
So compressing the gas literally speeds up the molecules inside.
Yes. You're adding energy to the system with the compression, which raises the average kinetic energy, and that's what we measure as an increase in temperature.
Okay, so that covers liquids and gases.
Yeah.
What about solids? Ice. How does the jiggling stop to make something rigid?
Well, it doesn't exactly stop. If you cool the substance down, you reduce the jiggling, less thermal energy. Eventually, the motion gets slow enough that the attractive forces can lock the molecules into fixed positions into a repeating pattern.
A crystal lattice.
Exactly, a crystal. That's ice. In a solid, unlike a liquid or gas, there's long-range order. Each atom has a specific place in this regular repeating structure.
And that structure explains the shape of crystals, like snowflakes.
Precisely. The internal arrangement, that repeating pattern, dictates the external shape. Ice has this specific structure, often leading to that familiar six-fold hexagonal symmetry we see in snowflakes.
And water's weird property. Ice floats. Most solids sink in their liquids.
Right. That's because the crystal structure of ice is actually quite open. It has built-in gaps or holes in the lattice. When ice melts, this rigid structure collapses, and the molecules can pack together a bit more closely in the liquid phase.
So liquid water is denser than solid ice. That's unusual.
It is pretty unusual, yeah. And one more key thing about solids. Even when frozen, the atoms aren't perfectly still. They're still vibrating, jiggling around their fixed positions in the lattice.
So even solid ice has moving atoms.
Oh, yes. Absolute zero temperature is the point where they have the minimum possible vibration, but it's generally not zero motion. There's always some quantum jiggling, actually. Helium's the really weird one. You need pressure and cold to make it solid.
Okay, this atomic picture is powerful. What about processes, like things changing? Evaporation.
Yeah, the atomic hypothesis explains that beautifully. Picture the surface of water open to the air. Molecules in the liquid are constantly jiggling. Every now and then, a molecule near the surface gets a particularly energetic series of bumps from its neighbors just by chance, like a lucky kick, giving it enough energy to overcome the attraction and escape into the air above.
And that's evaporation. One molecule at a time, breaking free.
Exactly. And think about which molecules escape. They're the ones that got that extra energy boost, right? The faster moving ones.
So they take more than the average energy with them when they leave.
Precisely. Which means the average energy of the molecules left behind decreases.
The liquid cools down.
That's why evaporation causes cooling. And it's why blowing on your hot soup works. You're pushing away the air that's already full of water vapor, allowing more high-energy molecules to escape from the soup, carrying heat away faster.
Huh. I never thought of it quite like that. Okay, what about dissolving something, like salt in water?
Another great example. First, remember, salt crystals aren't made of neutral atoms. They're made of ions-charged atoms. Sodium is positive, chlorine is negative. They're held together tightly in a cubic grid by electrical attraction. Now, water molecules, as we said, are a bit like tiny magnets. They have a slightly negative end, the oxygen, and slightly positive ends, the hydrogens. They're polar.
So the water molecules attack the salt crystal.
Sort of attack, yeah. The negative oxygen end of a water molecule is attracted to the positive sodium ions in the crystal, and the positive hydrogen ends are attracted to the negative chlorine ions.
Get the ions out.
They surround them and pull them loose, yeah. Wedge themselves in and carry the ions off into the water, Like evaporation, it's a dynamic process. Ions are leaving the crystal. And some might return, but if the water isn't saturated, more leave than come back.
It's all just atoms and molecules bumping and attracting.
Pretty much.
Yeah.
Which brings us to chemical reactions.
Hmm.
These are different because it's not just about phase changes or dissolving. Here, the atoms actually swap partners.
They rearrange into new combinations.
Exactly. Take burning carbon, like charcoal, in oxygen. Oxygen in the air exists as text-O2 molecules, two oxygen atoms strongly bonded together. Carbon atoms in the charcoal are bonded to each other. But it turns out carbon attracts oxygen much more strongly than oxygen attracts oxygen, or carbon attracts carbon. So when a text-O2 molecule hits the hot carbon,
It breaks apart the text-O2 bond and grabs the oxygen.
it does. They snap together, forming new molecules like carbon monoxide, CO, or carbon dioxide, text-O2, and breaking the old bonds and forming these new, stronger bonds releases a lot of energy.
And that energy release is the heat and light, the flame.
That's the flame. It's the kinetic energy from that atomic rearrangement. And this complexity can get, well, mind-boggling. Think about smell.
Like the smell of violets Feynman mentions.
Yeah. That scent comes from a specific, very complicated molecule, made mostly of carbon, hydrogen, and oxygen, but arranged in this intricate three-dimensional shape, like a puckered ring of 6 carbons with various chains hanging off it.
Just from carbon, hydrogen, oxygen? How did chemists figure that out?
Yeah. Incredible detective work over many years, figuring out these structures just by seeing how substances react, what they break down into. It was painstaking. Feynman notes that physicists were initially a bit skeptical that chemists could deduce these elaborate structures correctly.
But they were right.
Mostly, yes. Later methods, like X-ray diffraction, actually let us see the atomic positions and confirmed these incredibly complex arrangements the chemists had figured out.
Which is why chemical names are so long and terrifying.
Exactly, like that name for the violet scent component, 4,2,2,3,6, tetramethyl 5, cyclohexanol 3, butane 2,1. It's basically trying to be a verbal instruction manual for building the molecule, atom by atom.
Okay, so the theory explains a lot, but what's the direct proof? How do we know these atoms actually exist if we can't really see them?
Great question. The most famous piece of direct evidence is Brownian motion.
What's that?
If you put very tiny but still visible particles like pollen dust or fine soot, called colloids, in water, and look under a powerful microscope, you see them jiggling, constantly, randomly dancing around.
They're not alive.
No, not alive. They never stop jiggling. What's happening is that these visible particles are being constantly bombarded from all sides by the much smaller, invisible water molecules.
The water molecules are hitting them.
Yeah, billions of them, all the time. But because the water molecules are moving randomly, the hits aren't perfectly balanced. Sometimes the particle gets slightly more hits on one side than the other, so it gets pushed a tiny bit, then it gets pushed another way.
Like a big beach ball being jostled by a restless crowd.
Exactly. That visible jiggling is direct evidence of the unseen perpetual motion of the water molecules. It convinced a lot of skeptics.
And you mentioned X-rays confirming crystal structures.
Right. We can bounce X-rays off crystals, and the way the X-rays scatter forms patterns. From those patterns, we can calculate the precise arrangement of atoms, the distances, the angles, and those calculations perfectly match the shapes and properties of crystals we see in nature. It all fits together.
So, summing it all up, this atomic hypothesis really is the foundation.
It truly is. Feynman argues, pretty compellingly, that the most important idea in all of biology is simply that living things are made of atoms, and these atoms obey the laws of physics we've been talking about.
It's amazing how much complexity comes from such simple rules. Attraction, repulsion, constant motion.
And think about it. If simple, repeating arrangements of atoms like in steel or salt or water can lead to complex behaviors like waves or rust or the strength of a bridge,
Yeah.
then imagine the possibilities if you have an arrangement of atoms that is not simple and repeating. An arrangement that's different everywhere, constantly changing, incredibly intricate,
Right.
like the thing walking back and forth in front of you, as Feynman puts it, a fantastically complex machine built from these same jiggling atoms following these same basic rules.
That's quite a thought to end on. So the perpetual motion, the forces between atoms, explaining states of matter, evaporation, chemical reactions, it all hangs together.
It really does form the bedrock.
So maybe the final thought for you, the listener, is this. Given how much complexity emerges from these simple atomic rules, what's the most complex arrangement of atoms you deal with every day? And maybe, how much more is there still to discover out there, on the edge of what we don't know?
A great question to ponder. Thanks for joining us on this deep dive into Feynman's view of the atomic world.
We hope it gave you some new perspective. We'll catch you next time.